Thanks very much for coming. This is the first seminar of the year, 2016. And to start it, we'll start with somebody that's almost from the house, Gonzalo Muñoz. He's a PhD student at Columbia University. We're working with Dan Binstock over there. And he will be talking about his work there on lifting formulations for optimization problems with small tree width. Okay, thank you very much.
Thank you. So thank you for the invitation. So today I'm going to talk about this work that we've been doing lately of how you can exploit some sense of sparsity in a wide variety of optimization problems. The sparsity will be given by this parameter tree width that I'll define in a second. But for now, just think of it as a way of measuring some type of sparsity. So what's the motivation of this thing? We started working with this the so-called AC-OPF problem, which stands for, of course, AC, just alternate current, optimal power flow. The idea of the problem that you're trying to solve here is you're trying to decide how to operate a transmission grid. In a transmission grid, you can think of it roughly as a graph, where each node will be called a bus. And in each node, you'll have a voltage. Okay, voltage in this case is represented as a vector in R2 because it's a wave. Okay, and depending on the voltages on both ends of some line, you'll have some current flowing through it. That depends on this difference of voltages. So how this power equation look like? Given one line, you'll have two different powers. The power you can think of it as the power on this line that this guy sees. We'll call that PKM, and the other one PMK, which is not necessarily the same because there are some losses, for example. Okay. The equation for the current is a simple thing. It's actually a linear equation. All this G and B are just constant, and these are the differences of the voltages. Okay, so this part is fine. Oh, this J, by the way, is the complex number, the square root of -1. Sorry. However, the problem is that in this AC-OPF problem, you're not interested in the current. You're interested in the power, and the power is given due to Ohm's law by this equation right here, which is the voltage times this star is just the complex conjugate of this current. Okay, so this makes it hard because this formula that you have for the definition of power will actually be a quadratic. Okay, and it's not necessarily convex and so on. Yeah. So yeah, it's a complex number, but you can always think of it as an R2, right? You can think of it as a vector in R2. So yeah, so this here, E and F, is the voltage. So the voltage in node K is E comma F. Okay? And this will be just an equality of complex numbers, so you can pose it as two equalities, right? This stands for the active power and the reactive power. Okay? So what's the problem? We want to, so one version of this problem is just to look for feasibility, okay, of some setting. But the one that we're interested in is, which is the optimal powerful problem, is that you want to optimize the generation costs. Okay, so some nodes of some buses some nodes in the graph will be actually capable of producing some energy at some cost. In general, the cost function is fine. It's a convex quadratic function. So that part is okay. The problem comes from these equations that I pose here. So you want to minimize the production of power subject to some demands, and of course adding these equations that relate the voltages with the powers. Okay? So you have some limit on the powers that you can generate in each node. Okay, fine. You have some upper and lower bound on the norm of the voltages. So that's hard, but it's not the hardest thing. This defines a region that looks like a ring in the space of the voltages. And here is the problematic one. Okay, here I have this gives me the sum. This is just a way of writing the sum of all the lines that go out of K. Okay, and I want that is some sort of flow conservation type of constraint. So you add all the power that goes out of K, and you want that to be equal to the power generated minus the power demanded in that node. Okay, usually one of them is 0 for each node. Is just a general way of putting it. Okay, usually some nodes only have demand and some nodes can only generate. So this is the hardest, I would say, although we already have some non-convexities coming out of here. In general, this problem is it's NP hard. So Ohm's law gives me this equations right here, plus Kirchhoff's law, which is the sum of power that this flow conservation type of constraint. So these two things makes this problem a non-convex quadratic problem, and in general is NP hard. So it's actually strongly NP hard on general graphs, and it's weakly NP hard on trees. So it's already hard on trees. Okay, not the hardest, but it's still very hard. Because you're wondering how this weakly and strongly. Well, if you're not familiar with this, don't worry. It's just another way of dividing the NP hard problems. Okay, one of them, the weakly NP hards, is problems that are hard, but that have some dependency on the input, on the numbers. For example, knapsack. The hardness of knapsack comes from the actual coefficients. The strongly NP hards are the ones that are purely combinatorial. Okay. So we have a very hard problem, as hard as it gets. What do we do? And how do we deal with this problem? So the thing that we're grasped on is the fact that transmission grids are graphs of small tree width. I will define again what small tree width means, but for now think of it as the graphs roughly look like trees. Okay, they're not necessarily trees. You can have some clusters. Okay, but if you look at the big picture, it will resemble a tree. Okay, you don't have, I don't know, if you have a big country, usually transmission grids, you have a cluster, and then when you have another cluster, they're just joined by one line in a tree-way. Okay, they're not all connected. So we want to exploit that in this case. And recently, someone told us that actually gas networks are also graph of small tree width, and apparently there are interesting problems there as well. So we'll try to do something with that. And actually, some people have already started doing stuff with the small tree width in this problem, which is using using this sparsity in the SDP relaxation. Okay, so just in case you're not familiar with the SDP relaxation, what you do is when you have bilinear terms, you replace them with a new variable, and actually having this equality right here of this new variable being the product of two variables is equivalent of having positive semi-definiteness and rank 1. Okay? Yeah, they're real variables. So usually what you do in the SDP relaxation is you just drop this rank 1 constraint, which is the hard one, and you deal just with this one. That nowadays is people consider this easy to solve. Not really, but yeah, okay. But even if you consider that to be easy, in the case of this problem, this matrix are usually huge. So the constraint of this matrix being positive semi-definite is actually costly. So what people have been doing is using this sparsity that I just mentioned in order to chop this matrix into little pieces and just enforce positive semi-definiteness locally. Okay, I'll come back to this in a second, just to show you how it looks like. But the point is that people started doing this, and there's more and more literature in this sense, in SDPs. Okay, we'll try to do something different. We're going to try to just use LPs. Okay, so let me give you some definitions. First, the tree width, the thing that I'm going to talk about the most. So I'm going to give you two definitions. I hope one of them makes some sense. That's why I'm giving two, because they're kind of complicated, in my opinion. So the first one is, we say that a graph has tree width at most k if it's contained in a chordal graph with clique number at most k plus 1. Okay, so many definitions here. A chordal graph, you can think of it as a graph that is triangulated. Okay, a chordal graph is just a graph that whenever you have a cycle of length 4 or more, you have a chord. Okay, so you have an edge joining two vertices that are not adjacent. Okay, so that's why sometimes you can call this triangulated graphs. So you have your graph that you want to compute the tree width. You put a chordal graph on top of it, or you just triangulate that graph. Okay, you add edges, and you look at the clique number of that supergraph. Okay, that will give you an upper bound. The best way of doing that will actually give you the value of the tree width. Okay. Yep. Yeah. Okay. So this was defined during the 80s, and the important thing is that small tree width implies sparsity. Okay. And small tree width also allows a useful way of actually decomposing the graph, and that's the one that we will use. And actually, that makes another definition of the same thing. And bear with me, this is a bit dense, but I'll try to go with an example in order to show you all the steps. Okay, so we'll define what a tree decomposition is. So you take your favorite graph. A tree decomposition of it will be a pair TQ, where you have a tree, and Q will be, we'll call them bags, which are subsets of nodes of the original graph. So for example, here, you have your original graph, and you have this new graph with some properties that I'll show in a second, but each node of this tree will be sets of vertices of this original tree. Okay, so it's a way of grouping things and linking them in some way. So what do you ask for this decomposition to be actually a tree decomposition? The first thing is that every edge of the original graph must be contained in some bag. Okay, this is what they call the edge covering property. So for example, if you go to this one, you take any edge, let's say 2, 4. 2, 4 is here and here. It doesn't matter that it's more than one, but it has to be in at least one. Okay, is that fine so far? Okay, the next one, and which is the hardest one, is that if you take every vertex of the original graph and you look at the bags that contains that vertex, that will be connected. Okay, so for example here, node 4, if you look at the bags that contain node 4, they form a path. Okay, and you do that with all of them. Let's say 7 is contained here, here, and here, so it's connected. Okay, we'll see that in a second. Why is that useful? We say that the width of this tree composition will be the maximum size of the bag minus 1. Okay, you want the bags to be as small as possible, because you can always put the whole graph in one big bag, and that will be a valid tree decomposition, but it's too big. The idea is to have the bags as small as possible. Okay, so in this case, this graph has width 2. Okay, why is that minus 1? It's just because it's just so trees will have trees will have tree width 1. That's the whole point. But that minus 1 is not really important. And we call the tree width the minimum width of a tree decomposition. Okay, So the best one among all of them. Yes, so it's NP hard in general, but for constant width, it can be recognized in linear time. So there's an algorithm exponential in the tree width. That's it. I think it's like tree width to the tree width or something times n. So yeah, it's hard, but I think there are many heuristics that work very well. I don't know if there's any. I don't think there's any approximation that gives you some guarantee of how far you're from the tree width. But yes, I think many people, when they use this, they use heuristics in order to get something quick. Okay, any questions? Because this one is sometimes hard to get. The big point, the main point here is that just that we're dealing with a way of how you can decompose this graph in an order way. Order meaning that it contains edges and the vertices induce connected components. And we'll use this decomposition in order to solve problems. And actually, there was a lot of literature in the 80s where people exploited this low tree width in some combinatorial problems that are NP hard. And they solved that, and they proved that they can be solved in polynomial time, for example, when the tree width is bounded. Okay, so for example, coloring, you can color a graph. If you have the tree decomposition, you can color a graph in polynomial time. You can find the minimum coloring. And the way that they usually work, all of these algorithms, they are based on this notion of non-serial dynamic programming. So what they do is that with this graph, you group vertices in some way. So you can actually process them in an algorithm locally. And then since you have this connectivity with different vertices, you can actually merge them. And you can do like a dynamic type of algorithm in this tree and go, every time you go up a level, you merge the information that whatever it is you're trying to compute, and then you get a global solution. That's the idea in general. Okay, so how do we use all of this in an optimization context? So we're going to define something. This one is very easy: the intersection graph of a system of constraints. Okay, so now we're moving to the optimization setting. You have an optimization problem, and we're going to put a graph that represents something of that optimization problem. So we put a vertex for each variable, and then we connect those two vertices whenever that variable appears in a common constraint. Okay, so every constraint will actually induce a clique on this graph. Okay, and we'll call that the intersection graph. If, just to put some notation, if I is the instance, we'll call this gamma I the intersection graph. Okay. What? A clique, a fully connected thing. Yeah. Okay, so what we're going to do, just to paint you the picture, is that we're going to analyze what happens when this graph has small tree width. Is there something useful that we can do? Okay, this graph that represents the relationships of the variables in the system of constraints that we have. So what are contributions regarding this thing? So the first one that I'm going to summarize, because the proof is actually quite technical, but I'm going to give you the idea of how it works, is the pure binary case. Okay, and this was actually the basic building block that we're going to use in all the other results. So consider an optimization problem that looks like this: minimization of a linear objective subject to many constraints that are given by some oracle. Okay, in this case, it doesn't really matter what they are. They can be equations, they can be polynomials, they can be linear, whatever you want. However, I'm emphasizing here that each constraint does not include all variables. Okay, because remember, each constraint will induce in this graph something that is fully connected. Okay, and that it's bad for the tree width. Whenever that is large, that's bad. That's a bad thing. And we're assuming the opposite. We're assuming that this thing will be sparse. Okay, so if I have something that has all variables, that will immediately induce a clique, a huge clique. Well, the clique of a clique of all that connects all variables, and that will have a tree width, a large tree width. So here I'm emphasizing that it's just a few variables, okay, given by this set of indices, case of I, ki. So whenever we have this thing, we draw the graph, the intersection graph of this problem, which will have a clique for each one of these guys right here, for each of the support of this constraint. If this graph has tree width omega, then we can actually formulate this, and again, I'm emphasizing it can be any constraint. We can formulate this as an LP that has this many variable and constraints. So n 2 to the omega. So whenever the tree width is constant, this is actually linear. No, you'll see why. It's not that mind-blowing. No, anything. The constraints can be anything. It can be polynomial. It can be some oracle. So you just need something to tell you what if it's true or false, if something belongs to that set or not. You don't believe me yet? Yeah. So that's the thing. Yeah, exactly. So you'll see why we only need that. We started working with polynomials, and at some point when we did the whole thing, we realized, oh, you know what? We need only to evaluate the polynomial, and the polynomial, because that was the first thing evaluated. Yeah. So very surprising is a small LP, and the other thing, the important or weird thing, is that it doesn't depend on M. Okay, that confuses a lot of people. And a lot of people think that the M is hidden in the tree width somehow, but it's not necessarily the case, because you can fix a tree width and you can make up exponentially many constraints, and while keeping that tree width untouched. Okay, and at the same time you can have one constraint that involves all variables, and that will have large tree width. So there's no direct relation between M and the tree width. So what happened with M, where's this hitting? It's just in the time that it will take you to build this LP. Okay, so the time that it will take you to build this LP is roughly like 2 to the omega times M, plus some other terms. Okay. So how this works? So as Orlando said, the whole point is that since they're all binary and we have this decomposition of variables, okay, so this now groups variables, right? It's a way of grouping variables in some order. You can actually enumerate binary things, okay? So that's why there's a 2 to the omega there, because you enumerate all possible vectors with support here. Let's say you enumerate all vectors x1, x2, x4 for this bag that satisfy constraint that are supported only there, okay? So you look at the constraints that only have support in this thing, and you ask the oracle, does this thing belong to that set or not? Okay? So so the LP, what it does is that you'll have a bunch of this, for each bag you'll have a bunch of vectors that may or may not be extended to something feasible in the full support. So we merge them in some way. So how do we do that? We add a variable for each one of these feasible vectors that are contained in a bag, and you link them. How do you link them? You say, let's take, for example, A and B. A and B both of them have variable 2. So we want both of them to say the same thing of variable 2, because variable 2 is just one variable, okay? So what we do is say, okay, x2 will be equal to the, it will be a convex combination of these vectors that are enumerated, okay, this lambda v a, and at the same time will be a convex combination of vectors that are enumerated in b, okay. It will be a convex combination of guys here, and a convex combination of guys here.
When you build that graph from the email, when do you put an arc between two set of index?
Oh, so the arcs, they ensure that whenever you go, you fix a variable and you look at all the backs that contains it, it's connected. It's connected. It doesn't really matter where the edge is as long as you have that property. Okay? And the idea of that is that you have something that is linking them closely, and you're not saying something from x2. Let's say if x2 is here and x2 is way up here, they're saying two different things far from each other. That's the intuition of it. You have some sort of path between them, and you have some link, so you can link them. That's the idea. So what you do is you link them in this way. Unfortunately, it's not sufficient to only link them with this type of things. You also need to link them in. You also need to multiply them, and that's why the actual LP is not really that intuitive, because you also need to this. I put it as a bilinear term, but you don't really do that with the product. You linearize this thing. You linearize this thing, and you do that whenever there are there are variables that belong to two different bags. Okay, that's the idea. So the LP itself doesn't rely on this edges, on these connections, but the proof that the LP is actually correct and it will give you the actual answer will use these edges. Okay, the LP, you can just write it and it will work. Okay, that's for the binary case.
So you said that the role of the number of constraints of
yeah. Yeah.
You only for the construction of the lambda.
Yeah, exactly. That's why it's 2 to the omega times m, because you go over these things and ask whether it's feasible or not. So the next step was actually moving to polynomial optimization problems, where we also have continuous variables, which is the case of the AC-OPF problem I talked before. How do we deal with that? So the setting is the following. You have a minimization of a linear function subject to some polynomial constraint, not necessarily convex, can be anything. And variables belong to some mixed set, okay? Some of them are binary and the other ones are continuous between 0 and 1. And I denote as pi the degree of the maximum degree of a polynomial. So what we prove in this case is that if you do the same thing, you graph this, you take the intersection graph of an instance, and that has tree with omega, then you can actually have an LP of this size that now approximates the problem. Okay, now it's not something exact. Actually, you can argue that it cannot be exact, because you can always have you can have a polynomial problem where the only solution is, for example, an irrational number. That's easy to build. So you cannot really build an LP that will actually solve that. Okay. Yes. Yeah. The problem of the continuous variable. Exactly. So, well, this is what I was just saying, that unless P and MP, not even you do need this approximation, and also this epsilon dependency, it cannot be improved. Okay. So as you can see now, we have a 2 pi over epsilon to the omega, which is the bad term, and we really try to get rid of this thing. And this is what this theorem is saying, that you cannot really remove this. Okay.
What does it mean to solve the problem within a scale?
Oh, yeah. So what it means is that you will get a solution that will satisfy, is that instead of having fi greater or equal than 0, it will be greater or equal than minus epsilon times the norm of the coefficients of that polynomial. And you can actually prove that you need that as well. You cannot ensure greater or equal than minus epsilon in absolute terms, because you can always blow up everything. And if you were able to do that, you can solve problems, hard problems. Yeah, times minus epsilon times the norm of the. Well, the one we have is norm 1. So that's what that means. And how do we do that? How do we get this? Actually, very easy from the. Oh, sorry. Let me just. So I forgot about this. So there has been some related work in this with this polynomial optimization problem, but they usually involves constructing either SDP relaxations or SOS relaxations, and they also use this type of sparsity. Okay. Like I said at the beginning, you can, for example, the SDP relaxation, you can actually solve it better by not imposing the big matrix to be positive semi-definite, just pieces of it. And now that you know that there's an underlying tree decomposition, the way that works is that you do positive semi-definite per bag. That's the idea. And you can prove that that's sufficient to ensure the whole thing will be positive semi-definite. So this is, as far as we know, the thing that people have been doing the most in polynomial optimization. So there wasn't really anything with LPs, with approximating it with LPs. And how does this work? Like I said, it's very easy. You can actually take any continuous variable and approximate it. This is where the approximation comes from, with a sum of inverse powers of 2. Okay? So then, once you do that, you replace every continuous variable with integer variables, binary actually, and then you can approximate your polynomial optimization problem with a pure binary problem. And then you're back to the original setting that we had before. The only tricky thing is how do you handle this error in order to get the error I told you about, this scale feasibility, whatever. That's a hard part, but the idea itself it's very easy. And the other thing is, why does this work? Is because if the polynomial optimization graph had tree with omega, then the new graph, the graph that you get in this pure binary, will have this tree width. Because you just need to expand. You can take the same tree decomposition, and whenever a variable appears, you replace it by its corresponding expansion. So you only get this omega times L. Okay, and that's basically why everything else appears. All these other terms appear. No. Well, you replace a variable. Well, yeah, you replace a variable. You split it into in the graph. You split it, and you draw a clique in that. But you don't really need to do that. You can actually just take the tree decomposition and do the same thing. You can prove that it will be valid as well. Okay, so that was the whole thing with polynomial optimization. And just to finish. Yeah. Oh, you mean the fact that I moved from oracle to polynomials? Yeah. So that is only so it's not for the tree width. It's in order to measure the error. That's the whole thing. Because when you have a polynomial optimization problem, now that we're approximating it, you need a way of measuring how far you are from a feasible solution, and that we're only able to do that with polynomials. Okay, so the last thing I'm going to talk about is something we call network mixed integer polynomial optimization problems. Because actually, I kind of lied to you the whole time, because I gave you a motivation that was a problem that already had a graph. But in all the things I've said now, I've drawn a graph from the formulation. It's a different thing. And you can actually prove that they're completely different, and I will show you in a second. So AC-OPF problem was not really, we're not done with AC-OPF with the polynomial optimization problem. We need something that takes into account a graph that it's already there, okay? And let me give you an example of why this is bad. Take, for example, a star, and you want to supply something to the center of the star. Toy example, ridiculous, but it will show what I want to say. Let's say we want to do that. You can give that problem to any, I don't know, master student, and they will be able to formulate it with a flow conservation type of constraint, right? Where you have the sum of everything that is produced around the star equal to some demand at the center, okay? The star is a tree, has tree with 1. The graph somehow, the problem somehow comes from this graph. However, when we pose this constraint and then we take the intersection graph, that will have a clique of size n-1. So we'll have large tree width. So we lost everything in terms of tree width that we got from this graph. And that can happen also in the AC-OPF problem as well. So we want to figure out a way of actually inheriting the original tree-like structure. Okay, how do we do that? So first of all, let me define what a problem over a graph is, that we call NPO. So we're giving an undirected graph, and for each node, we'll have some set of variables. They need not to be disjoint. It's perfectly fine. But it's important to think, to keep in mind that there are many of them. There can be many of them in each node. For example, in the AC-OPF problem, those were the voltages. Okay, so we define the problem as in this nasty way, but let me show you a picture so you'll get an idea. So we define a problem over a graph, a problem where every constraint will consider a sum over all the neighborhoods of some node, okay? And for each edge, I'll have a polynomial that will involve variables from here and from here, okay? So exactly in the AC-OPF problem, this was voltages, 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 voltages everywhere. The power flowing through a line was given by a polynomial over only these 2 voltages, nothing else. And then you sum all of them, okay? So that's why I call an NPO. You minimize linear function for now, that's fine. So, and subject to constraints that look like this. For every vertex, you have a sum over the neighbors of polynomials that depend on the endpoints, on the variables on the endpoints. Okay? That's what I call an MPO. Very general as well, I think.
The first problem with the star is not the same expression.
It is.
The one with the sum from x2 to x.
Yeah, it is one, because you have a variable for each one of these guys that will produce this. Yeah, so this you can associate this constraint to the center node. Yeah. Yeah. Exactly. So what we proved in this case is that if you have an NPO, a network, blah, 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 over a graph, again, this is different from the intersection graph. There's already an underlying graph there, and that graph, I say that has tree width omega. Then, as in the polynomial case, I can approximate it to scale feasibility and optimality tolerance with an LP of this size. So before, we had 2 pi over epsilon to the omega. Now I lost the omega, but I replaced it with an O of omega times k. This is fine. This is the number of variables that are in some given, the maximum number of variables in a given node. Okay, in some node. This part is fine. We were kind of expecting this, of course. But so in order, what we were losing from going from the underlying graph to the intersection graph will be an O of. It will be a constant term. Okay, and that's a nice thing because we don't. In the star example I gave you before, we went from 1 to n, and what we show is that you don't need to do that. You can go to some constant. Okay, to some constant factor. And as a corollary, we can approximate this AC-OPF problem with an LP of this size. It's just because the number of variables in the number of variables and the degree in this problem, in this family of problem, is constant. Okay, that's it. So just again to give you the intuition of how this thing works, the problem relies on the fact that this guy has too many neighbors. Okay, because whenever you have a sum over this thing and then you take the intersection graph, this will all be connected. It will induce a clique here. Okay, so what if we split it? Okay, the degree was n, but now we can split it into many things, all of them with degree 3. You can actually do that. In this star example, you can easily do that. You put these new variables that are the cumulative sums, and you can replace this constraint into many constraints that involve these new variables, and all of them will only involve three variables in this case. You can prove that this thing is equivalent to this. Okay, it will give you the same solution. It will not be the same problem, but it will be equivalent. And actually, this thing right here, the intersection graph, will have width 2. So just by doing the splitting, instead of going from tree width 1 to tree width n, we went to from tree width 1 to tree width 2. And then we can apply the same thing. Okay? Any questions? So that's the whole point. What? So, yeah, so no, but you need the original graph to have small tree width. So what I'm saying is that you can go, if you start from a graph that has small tree width, then you can transform it into a problem where that new problem has tree width that depends linearly in the original one. So you cannot really decrease this splitting. When you do splitting, you cannot decrease tree width actually. You can only increase tree width. The tricky thing is that you don't need to go very far. You can just go up to a constant factor of the original tree width. Okay. So as I said before, the big problem is high degree vertices. The problem in general, even though it sounds great that we just need to split, is that splitting them in any way, it can drastically increase the tree width. Okay, you might not inherit everything. So this example, and then here you must trust me in the values I'll give you. This graph right here, which is a path, one node, another path, one node, blah blah blah. This thing has tree width 3. However, if you split this vertically, this intermediate nodes, you'll get a square grid. And this thing has tree width k. Okay? This is very far from being a tree. So you don't need to, so it's not sufficient to only split. You need to split in an intelligent way. And that's the tricky part of this part of our work, is that we prove that there is a careful splitting that you can do that does not increase the tree width too much. So you can go from something, you can replace all the high degree vertices with low degree vertices by splitting them in this careful way. So in the previous example, instead of doing this vertical splitting, you can actually do first split them like this, horizontally, and then vertically, which seems very random. But only doing that, you'll get a new graph where now you don't have these edges right here. There's none of them, only one, and you can prove that this also has small tree width. Okay? So that's the whole point of what we prove in this part. So we did 2 steps. So the first thing is that if you have a problem over a graph that has tree width omega, then you can split this thing and get an equivalent problem over another graph after you did all the splitting, where the tree width is linear in the original one. And additionally, the maximum degree of that new problem will be 3. Okay? So that's the first thing, this careful splitting that we did. And then the next step is that once you have a problem with some tree width and additionally has maximum degree 3, then the problem itself, when you take the intersection graph, blah blah blah, and all this thing I've talked about before, that will have small tree width as well, also linear in this omega, and now times k, which is the number of variables. Okay, so if you compose these 2 things, you get the result that we had before. So again, you just split them and you reformulate the problem, and you get something that has small tree width. So for example, in the AC-OPF problem, what we're doing is transforming the AC-OPF problem into some equivalent problem that is actually not an AC-OPF problem, because we will have some equations that are not related to current and whatnot. But it will be equivalent, and if the original problem had small tree width, the new one will have small tree width as well. Okay, any questions? Okay, that was it. Sorry. Thank you.